Previously, we discussed how to explain lift using Newton's third law of motion, but you can explain lift just as well using the Bernoulli's principle, which states that within the flow of a fluid, points of higher fluid speed will have less pressure than points of slower fluid speed. For example, when you constrict a flow, pressure will build behind the constriction and the fluid will move faster where it's constricted. This is just another way of saying that a fluid will speed up if there's more pressure behind it than in front of it. Think of when you pinch a garden hose to send it further. However, Bernoulli's principle gets a bad rap because of the equal transit time theory, which we know to be false. Let's get this false version out of the way. According to the equal transit time theory, air separated at the stagnation point to either flow above or below the wing must meet at the trailing edge simultaneously. Considering a wing normally has a convex curve on top with a flat bottom, for this to occur, air above the wing must cover more distance in the same amount of time, which can only mean that air above the wing must travel faster than below it. And since Bernoulli's principle states that fast-moving fluids have lower pressure, pressure above the wing must be lower than below it, creating lift. This was how lift was taught in the past, and I'm sure many of you learned it this way as well. However, thanks to experiments done by scientists, we now know that air above the wing travel much faster than below it and that they simply don't meet up. This directly contradicts the equal transit time theory, and because of this new knowledge, many have forsaken Bernoulli's principle as a way to explain lift. However, it's the equal transit time theory that's wrong, not Bernoulli's principle. So if we can't use the equal transit time theory to explain faster flow speed above the wing, how do we do it? Simple. Remember the garden hose and how when a flow is constricted, its speed increases? If you look closely, the upper portion of the wing constricts airflow above the wing just like how someone's finger constricts the tip of the garden hose. Consequently, airflow speed increases and Bernoulli's principle tells us that pressure will drop to create lift. Now someone might point out lift described using Bernoulli's principle doesn't explain how symmetric or flat wings fly, or how airplanes fly upside down. This critic is imagining a situation where there's no constriction or it occurs below the wing and not above it. At first, it might seem the critic has a valid point. However, in such situations, the stagnation point isn't where the critic thinks it is. In case of the flat wing, the stagnation point is not at the tip but below it, and in case of an airplane flying upside down, the stagnation point shifts to a lower location. In both cases, constriction still occurs above the wing as well as lift. So the next time someone tells you Newton's third law of motion is the only and actual way of explaining lift, tell them it's the equal transit time theory that's wrong and not Bernoulli's principle as a way to demonstrate lift, which as you just saw explains lift just as well as Newton's third law of motion. Stick science. Thank you for watching. If you missed out on how you can explain lift using Newton's third law of motion, click here.